Hello students, welcome to the next lecture on the complex analysis. Today I will explain you the concept of the residue with the help of 20 plus numerical examples. Myself Dr. Harish Garg. You can follow and subscribe my YouTube channel where you can find the playlist of the complex analysis. You can see our last lecture was on the Rauchi theorem, argument principles and many more lecture available in this playlist. You can follow and subscribe my YouTube channel. Now, we all discussed that the lecture of the singularity where we have learned if f is isolated singularity at the point z is equal to z naught, then we can expand the function fz in terms of the Laurent series, where the component or the term which are associated with the negative power of the n is known as the principal part of the function, and the value of the bn is defined as 1 over 2 pi iota into integrations fz over z minus z naught, and the value of the an you can easily obtain with the help of the value of the bn by using an is equal to b of minus n. That means you can replace the value of the n to be the minus n, then it comes to be an. Clearly say the value of the b, and if you open that, it will be my b1 over z minus z naught plus b2 divided by z minus z naught square and so on. This value of the b1, the particular value of the b1 will play a very specific role in the complex analysis, and the value of the b1 is known as the residue of the functions. So can you define the value of the b1? I can substitute the value of the n in this equation. You will get the value of the b1 is 1 over 2 pi iota integration of the curve fz into dz. So this is the concept of the residue that we will discuss in this lecture. So as I mentioned you how you can define the residue. So the first definition is you can calculate the value of the b1 by using the equation number 1 by substituting n is equal to 1, or you can also see if I open this bracket, it will be b1 over z minus z naught plus b2 divided by z minus z naught square and so on. So clearly say b1 is the coefficient of 1 over z minus z naught in this function fz. So you can use either of the definitions to solve the problem. Now how you can compute the residue of the given functions. So we will discuss the two different cases. The first case is when the function has a simple pole. Second case is when the function is of the pole of order m which is greater than 1. In this lecture we will cover all those cases in which the function has a simple pole. How you can calculate the residue of a simple pole? First of all, you can note down this formula on your copy, and then I will explain you their proof and then numerical example. Residue at the point z is equal to z naught is defined as limit z approaches z naught into z minus z naught of fz. The proof is a very simple, or otherwise you can also use as the coefficient of the 1 over z minus z naught. How you can prove that? It's a very simple. It is given that a function is of the simple pole. That means I can write the function is b1 over z minus z naught plus summation an into z minus z naught raised to power n. Because it is of the simple pole, so that means the power degree must be 1. So this implies, can you find the value of, can you find the value of the b1? So clearly say b1 will be, I can multiply z minus z naught on the both side, and I can take this value on the left hand side. So this number will be an z minus z naught raised to power n plus 1. Now you can take the limit as z approaches z naught. This value will be my 0. Hence the b1, that is a residue at the point z naught, is my limit z minus z. Is it clear everyone? So based on these simple definitions, I can solve you the 15 plus examples in this video. I hope you can like and comment on this lecture as well. A very beautiful remark for you which are very useful for the CSR net as well as the GATE examinations. If the function is my analytic, then the residue value at the point z naught of the fz is 0 always. Remember, if the function is analytic, then the residue value is always 0 provided your z naught is my finite point. Fine. The finite point means the value of the z naught may be half, it may be minus of 3, it may be pi over 2, or it may be anything. But z naught is not equal to infinity. Fine. So whenever z naught is a finite, then the residue will always be the 0 whenever function is analytic. On the other hand, the function may be analytic at infinity, but the residue is non-zero. Can you provide the example? We already discussed in our Cauchy integral formula. That means if you consider the function fz is 1 over z minus z naught, then clearly say z is equal to z0 is a simple pole, and the function values at this point will be infinity. That means the function is analytic at the point infinity, because what is the value at the infinity? This value will be 0, and hence it's a finite number, therefore the function is analytic. But can you find the residue at the point infinity? Residue at the infinity is minus 1 over 2 pi iota integration of this. Can you find the value of this integration? I can use the Cauchy integral formula. The Cauchy integral formula will give you 2 pi iota. So hence the residue is my non-zero, even the function is my analytic at the infinity. Remember, this is a very important point. Remember, this point is only for the finite point, but this is not the finite, so the residue may be non-zero. Now let's start with the numerical example. Look at that. Always remember, whenever your target is to find the residue, find always, firstly you can always find the value of the pole. How you can find the pole? You can substitute denominator value to be 0. So can you find the pole of this function? So the pole of the fz, I can substitute denominator is my 0. That means z is equal to 1, which is of the multiplicity is 1. So therefore z is equal to 1 is my simple pole. Fine. Once we can get the simple pole, then we can find the residue is limit z approaches 1, because the pole is my 1, z minus 1 into fz. So this is my residue at the point z is equal to 1. So can you substitute the value of the fz? If I substitute the value of the fz in this equation, z minus 1 will be cancelled. So the answer is my 1 is the right answer of the problem. This is the first method you can use by the definition of limit. Or we all know we can also calculate the residue, which is coefficient of 1 over z minus z naught in the function fz. Fine. But I always recommended you can prefer the first method whenever there is a simple pole. But I will tell you the second method as well. Our target is to find the coefficient of the 1. So I can write the function is, what does it means? Wherever the z return, you can write in terms of the pole. Pole is my 1. So you can always write in terms of the z minus 1. The denominator is fine, but I can replace the value of the numerator is z minus 1 and then plus 1. Fine. I can separate them, plus 1 over z minus 1. Now you can see what is the coefficient of the 1 over z minus 1. The coefficient is my plus 1. So therefore the residue is my plus 1 is the right answer. And you can see in the both the cases your answer is same. Okay, determine the poles. Can you find the pole of the function? The pole of the function is, you can substitute denominator value is my 0. Fine. So how you can find the denominator? So the value of the pole is my z is equal to 1, 1. Correspond the second value, z is equal to minus of 2. Clearly say z is equal to minus 2 is my simple pole. Fine. And z is equal to 1 is pole with the multiplicity 2, or you can call as the double pole. How you can find the residue about the double pole? that we will discuss in our next lecture, because the today's lecture is only on the single pole. Fine. Now your target is to find the residue at the simple pole. So how you can find that? I can use the limit z approaches minus of 2, z minus z naught minus minus plus 2 into f of z. Fine. I can substitute the value of the fz. You can see z plus 2 will be cancelled out. So the answer becomes limit z approaches minus of 2, z square over z minus 1. So I can substitute the value. It's a 4 over minus 3. Minus 4 over 3 is the minus 4. Sorry, it is my square also. So this is minus 3 square. That number is 4 over 9 is the right answer of the problem. Look at another one. Find the residue at its pole. Can you find the pole? Pole means the denominator part is 0. Therefore, z is equal to 2 and z is equal to 3. Both are my simple pole. How you can find the residue? I can use the definitions. So this value will be limit z approaches 2, z minus 2 into fz. And for the second case, you can see limit z approaches 3, z minus 3 of fz. I can substitute the value of the fz. It becomes limit z approaches 2. I can substitute the fz. Z minus 2 will be cancelled out. It's a z square. Sorry, it's a z square. Fine. Divided by z minus 3. So if you substitute them, it is 4 over minus 1. Similarly, for the second case, you can, or if it is a cube, you can write as a cube. Then the answer will be 8 over minus 1. Minus of 8. If it is a 3, then 27 over 1 is a 27 is the right answer of the problem. This number is my cube. Look at the next one. Find the sum of the residues. Your target is to find the residues at the pole inside the circle. Can you draw the curve? The curve is my circle, radius 2. Fine. Now, can you find the pole of the functions? How you can find the poles of the fz? I can substitute the denominator value to be 0. So z into cos z is 0. This implies z is equal to 0 or cos z is equal to 0. This implies z is equal to 0 and cos value 0 will be my 2n plus 1 pi over 2, where n is my integer. I can substitute the value of the n. When n is 0, it is my plus minus pi over 2. N is equal to 1 plus minus 3 pi over 2 and so on. Fine. Now out of these poles, which one lies between the circle? 0. Yes, it lies. Pi over 2. That number is 1.57. 1.57 minus 1.57. 3 pi over 2. That will give you the 4.7 something. That lies outside. This means you have the only the 3 poles, that is a 0, plus pi by 2, minus pi by 2, and all are my simple poles of the function fz. Now how you can find the residues? Again, I can use the definition z minus z naught. I can substitute the value limit z up 0. What is the value of the fz? Fz is my sine over z, sine z, divided by z into cos z. So z will be cancelled out. So sine is a tan of 0. What is the value of the tan of 0? Tan 0 is my 0. So the residue at the point 0 is my 0. Similarly, for the second case, I can substitute the values. Limit z approaches pi by 2. Z minus pi over 2 is a sine of z divided by z into cos of z. Now clearly say if you substitute pi by 2, cos pi by 2 is 0. It is my 0 by 0 form. Once it's a 0 by 0 form, I can apply the L'Hopital rule. How you can apply the L'Hopital rule? I can differentiate the numerator and the denominator. So firstly, I can differentiate the denominator 1 into cos z minus z into sin z. I can numerator 1 into sin z plus z minus pi over 2 cos of z. Why? Because this is my 0 by 0 form. Fine. Now you can substitute the value. Once is a pi by 2, this value will be 0. This value will be 0. Sine pi by 2 is 1. It is minus pi by 2 into 1. So the answer is minus 2 over pi is the residue. Similarly, can you find the residue at this point? I can substitute the value of the fz, sin z over z into cos z. Again, you can see when you substitute z is minus pi by 2, this limit is again 0 by 0 form. Now you can do the calculation. Again, I can use L'Hopital rule, 1 into cos z minus sin z into sin z. This value will be 1 into sin z plus z plus pi over 2 into cos z. When you take z is minus pi by 2, cos, this value will be 0. Cos value will be 0. Sine of minus pi by 2, sine of minus pi by 2 is my minus 1. Minus pi over 2. Sine of minus pi by 2 is again minus 1. So the answer is minus plus is a plus 2 over pi is the right answer. Now your final target is to find the sum of the residues. So you can find the sum, that is a 0 minus 2 over pi plus 2 over pi. Answer is my 0 is the correct answer. उम्मीद करता हूँ आप वीडियो को लाइक और कमेंट जरूर करेंगे. Look at the next questions. Find the residue of the functions on the circle. So you can draw the circle. This is the first method I can tell you with the help of the poles. Fine. I will upload the part 3rd of this residue. You must watch on the residue problem part 3rd as well, where I can define the special functions. Whenever it's a cos of z, whenever it's a e of z, whenever it's a tan inverse of z, we all call as the special functions. And how you can find the residue of the special functions, that we will see in our part 3rd. Anyhow, can you find the pole of the functions? The pole will be sine of pi z is 0. This implies pi of z will be 2n plus 1 pi over 2. Value of the z will be 2n plus 1 over 2. N belongs to the integers. So that means when you substitute 0, answers are plus minus, then plus minus 3 over 2 and so on. So out of these values, which one lies on the unit circle? Only plus half minus half lies inside the circle, and clearly say these are my simple poles. Again, by using the definitions, I can substitute the value of the fz. Fz is my e raised to power z over cos pi z. When you substitute half, the numerator becomes a 0. Cos pi by 2 is 0. Again, it is 0 by 0 form. Again, I can apply the L'Hopital rule. So after applying the L'Hopital rule, the numerator part becomes 1 into e raised to power z plus z minus half e raised to power z, and the denominator becomes minus pi sine of pi into z. Now you can substitute half. This value will be 0. The numerator becomes e of half. Sine of pi by 2 is 1. So the answer is e raised to power half minus pi. Similarly, you can find it by own, and after the calculation you will get the answer is e raised to power minus half divided by pi. Find the residue of the functions over these three different circles. Firstly, can you find the pole of the functions? How you can find the pole? That is z square plus 2z plus 5 is equal to 0. The value of the z will be minus of 2 plus minus b square minus 4ac divided by 2. This number will be minus of 2, 16. 16 will be by 4 divided by 2. That means answers are minus 1 plus minus 2i. Now look at the first part. On the given circle z is equal to 1. Can you say the point? Where is the point lies? Minus 1 plus 2 iota, minus 1 minus of 2 iota. Look at that. Where is the minus 1? This is the value of the minus 1. This value is my plus 1. This value is my minus 1. Now where is the minus? How you can write that? This coordinate is my minus 1 comma 2. So where it lies? It lies here, because this value is my 2. So this value is lies outside the circle. Similarly, minus 1 minus of 2, again this value lies outside the circle. So that means none of the point lies inside the circle. That means this function is my analytic. This function is my analytic on the given domain z is equal to 1. So therefore the residue is my 0. Fine. Look at the second. How you can do that? How you can draw the circle? Always compare them. Z minus a is equal to r, where a is my center. So can you find the center? Center is my minus 1 plus iota. So how you can draw that? The coordinate is my minus 1 comma 1, minus 1 comma 1. Fine. Sorry, x is my minus 1, y is equal to plus 1. This is my center. Radius is my 2. This is my minus 1 comma 1. So you can draw the circle of radius 2. Now check whether, now clearly say this value lies inside. How? You can substitute the value in the given function. Minus 1 plus 2 iota plus 1 minus of iota. Check whether this value lies less than 2, then it lies inside. If this value is my greater than of the right hand side, then it lies outside. If this value is equal to 2, then it lies on the circle. So clearly say this value will be my iota. The modulus of the iota is my 1. 1 is less than 2. Yes, it lies inside. On the other hand, can you say whether this value lies inside the circle? So minus 1 minus 2 iota plus 1 minus of iota. This is minus 3 iota. Modulus is my 3, which is greater than 2. That lies outside the circle. So once it lies outside the circle, we can start with the only residue at this point. How you can write the Fz? Now you can see you have the two different poles. So I can write this number is 1 and z plus 1 plus of 2 iota. If I substitute the value of the Fz, you can see this number will be cancelled out and the only part becomes z minus 3, z plus 1 plus 2 iota. Now you can substitute the value minus 1 plus 2 iota minus 3 divided by minus 1 plus 2 iota plus 2 iota. So that will be my 2 iota minus 4 divided by 4 iota minus 1. Fine. Now because we all know we can never put denominator as a iota. Where is a z plus 1? Sorry, it's a plus 1 also. So 1 will be cancelled out. It's only 4 iota. Then you can multiply by 4 iota, or you can simply multiply by iota. You can get the answer as iota plus half. Similarly, for the third case, check whether z is equal to minus 1 plus 2 iota or z is equal to minus 1 minus of 2 iota lies inside the circle. So firstly, I will check about the first case. Minus 1 plus 2 iota plus 1 plus iota. This number will be 3 iota 3, which is greater than 2. That lies outside the circle. Look at the second one. Minus 1 minus iota plus 1 plus iota. This will be my 1. This will be because this iota minus iota is iota which is less than 2. That lies inside the circle. Again, once is a simple pole, we can start with the residue. I can substitute the value of the Fz. I can break into the two components and you can substitute the values as z is minus 1 minus 2 iota plus 1 minus, so 1 will be cancelled out. The numerator becomes minus 4 minus 2 iota divided by minus 4 iota. You can make them as a separate. It is 1 over iota plus 1 over 2. Answer is half minus iota. Look at the next one. Find the residue of the functions at the point z is equal to iota a. So we will firstly check what is the order of this pole. So we can find the pole. Fine. How you can find the pole? You can substitute denominator as a 0. So that means z is equal to iota a, z is equal to minus iota a, and both are my simple pole. And your target is to find the residue at the point iota a. So I can use the definition z minus iota a into fz. I can substitute the value of the fz. You can see this value will be cancelled out. The only expression becomes z square divided by z plus iota. I can substitute the value of z is iota a plus iota a. Numerator becomes minus a square 2 iota a. I can rationalize them. It will be my a over 2 is the, I can rationalize them, iota divided by iota. So its iota square is a minus 1. So a over 2 iota is the right answer of the problem. Find the pole, find the order of the each pole and its residue. Can you find the pole? Clearly say the poles are my 0, 1 and 2 and all are my simple pole. Once is a simple pole, we can start with the residues. So you can start with the first case, z approaches 0. I can substitute the value of the fz. The z will be cancelled out. It's a 1 minus 2z, z minus 1, z minus 2. Now you can substitute the value. You will get the answer is z is equal to 0, minus 1, minus 2. Answer is half is the right answer. Similarly for the second case, you can substitute the value of the fz. So that value becomes 1 minus 2z divided by z into z minus 2. I can substitute z is 1. The numerator is minus 1. This is 1 and this is minus 1. Answer is plus 1. Similarly, you can compute the third value by on and you will get the answer is minus 3 over 2. Find the residue of the functions at the point 1, 2, 3 and infinity and finally show that their sum is 0. Again, very simple. You can start with the pole. Clearly say the poles are my 1, 2 and 3. All are my simple pole. Then we can find this residue at the simple pole. Z approaches 1. I can substitute the value of the fz. Z minus 1 will be cancelled out. Z minus 2, Z minus 3. Similarly for the other cases. Now you can substitute the value. It's a 1 minus 1 minus 2 is a 1 over 2. 8, 2 minus 1 is 1, 2 minus 3 is minus 1, minus 8. And similarly for the third case, you will get the answer as 27 over 2. Now the question arises is how you can find the values at the infinity, because infinity is not the value of the finite. Fine. So I will explain you in detail how you can find the infinity value, but right now you can use either of the formula. Residue at infinity is a limit z approaches infinity minus z fz provided the limit exists. Otherwise we can use as minus coefficient of the 1 over z. So firstly if I try to use this formula, that means I can multiply the value of the fz by z. So if you look about that, if I multiply this value, it is z4 divided by z minus 1, z minus 2, z minus 3. Fine. And I can take the limit z approaches infinity of the negative limit. So do you get the finite answer? No. Why? Why it's not a finite answer? Because the degree of the numerator is greater than of the degree of denominator. So the answer will always be the infinity. But this method is applicable only when the limit is my finite. Fine. So it means this method is not applicable for this particular problem. I will explain you the residue at infinity in the separate video. I will upload after that. So till then you can find the residue by using the coefficient of 1 over z. So can you write the given function fz in terms of the 1 over z? So I can take z is common. It's 1 over. For the second term I can also take an is common. So from the third term I can also take an is common. Fine. So clearly say z cube will be cancelled out. I can write in terms of 1 minus 2 over z minus 1, 1 minus 3 over z minus 1. Fine. Now you can expand the series. What is the series of the 1 minus x? It will be 1 plus x square plus x cube and so on, provided absolute value of the x is less than 1. And clearly say our target is at infinity. So 1 over infinity is 0. Now you can open them. It's a 1. Because we need only as a coefficient of the z, I can write only first two terms, plus 2 over z plus 3 over z. Now if you open this bracket, constant term is only 1, coefficient of the z, if you multiply this value, it's a 2 over 3, 2 over z, 3 over z. So that value will be 2, 1 plus 3 and so on. So this number will be my 6 over z. So can you find the coefficient of the 1 over z? Coefficient of the 1 is my 6. So the answer at the infinity is my minus 6. Now we get all these residues and show that the sum, you can add them, it will be my 0 is the right. Look at this another one. Find the residues at the simple pole. So firstly you can find the pole by taking denominator as a 0. So clearly say the pole is corresponding, the first part is a minus of 2, which is of double pole. Why it's a double pole? Because the power is my 2. Correspond the second case, this is my 2 single, it is my simple pole. Corresponding the third is again my simple. Fine. And our target is to find the residues only at the simple pole. That means at the point 2 and 3. But don't worry. I will explain you how you can find the residue in my part 2 lecture. Fine. This is my next lecture, but don't worry, I will upload very soon. In this lecture, we are trying to able to learn the single pole. So let's start with the limit again. Limit z approaches 2. I can substitute the value of the fz. Z minus 2 will be cancelled. It is z cube divided by z plus 2 whole square, z minus 3. Now you can substitute the value of the 2. Z is 2, 8, 4. 4 square is my 16. 4, 2 minus 1. So minus half is the residue at the point z is equal to 2. Similarly, at the point z is equal to 3, I can substitute the value of fz. Z minus 3 will be cancelled. Now you can substitute the value of the z is 3, 23. 5 square is 25. 3 minus 1. So 27 divided by 25 is the right answer. Find the pole of the functions. Again, you can see this is my special function. Fine. So I will upload the part 3rd on the residue to solve how you can find the residue of the function in the easiest way. But in this lecture, I will also explain you. This is the first method. Fine. Second method, I will explain you in my part 3rd of this video. Can you find the pole? Z is equal to n pi, where n is my integers. Fine. So that all are my simple pole. Therefore, limit residue at the value of the n pi, z minus n pi into fz. Fz is my cot. So I can write as a cos z over sine of z. Fine. Now clearly say this is my 0 by 0 form because sine of n pi is 0. So I can apply the L'Hopital rule again. So what is the denominator is? It's a cos of z. Numerator is 1 into cos z plus z minus n pi into minus sine of z. So when you substitute n pi, this number will be 0. So cos n pi is my minus 1 raised to power n over minus 1 raised to power n. Answer is 1 is the correct answer of the problem. Again, you can see this is a sine function. Again, this is special functions. Thus, we will discuss the first method in this lecture, while the second method we will discuss in the part 3rd of this residue. We can find the pole. As usual, the pole is my n pi. We can start with this case. Substitute the value of the fz. Again, it's a 0 by 0 form. So I can find the limit by using the L'Hopital rule. The denominator becomes my cos z. Numerator becomes 1 into z plus z minus n pi into 1. So clearly say when you take n pi, this number will be 0. So answer is n pi. Cos n pi is minus 1 raised to power n. Why? Because cos of n pi is minus 1 raised to power n. So minus n pi over minus 1 raised to power n is the right answer of the problem. So you can see that, remember that student, this is the first method by using the pole. But I will tell you in the my part 2nd, part 3rd, where you can find the special functions, how you can find that's quite easiest way. So I hope you can enjoy this session too. We will see the next lecture on the pole of order m which is of greater than 1 in our next lecture. Till then, you can like and comment on this video. You can share this video with your friends. Best of luck, students, and thanks for the watch.